Okay. Today we're going to study vector fields. Okay, first of all, we have to understand what is vector in mathematics. And let's understand in two-dimensional case. Okay, a vector without a vector in physics is just an object. Okay, a vector in the space. Okay, on a plane. Okay, it's just a segment was a direction, a starting point. This is called a vector. Okay. Now, if we have a vector in the xy coordinate, okay, those are the vectors. Okay, so if a vector in the xy plane, so now in the plane, you have a coordinate system there. Okay, how to describe a vector? Okay, a typical notation will be as follows: a v. Okay, use this notation. Okay, this means those are the components of the vector. Then how do you draw it? Okay, and when you draw the vector in the xy plane, you find out you have to choose a starting point and an ending point, right? So this will be the vector. Okay, here, the starting point at the origin. Okay, this is the vector in the standard position. But we can draw the v, the same v. It's actually the family of objects in the space, in the xy plane. They are all parallel, but the starting point will be different. You just move the same object over this way. Okay, those are also called the vector v. Okay, so don't be confused. Yeah, that's really not a very precise definition because it's mixed up with a terminology in physics. Okay, so if I draw the vector, okay, okay, how to describe vector in mathematics? You can only use two numbers to describe. If you use two numbers, and this is a point corresponding to two numbers, so that's if you it as an end point, then your starting point will be the origin. Okay. Okay. Now, if I want to draw this vector at at a particular point, okay, then I choose that point as a starting point. Here's x and y. Okay, so this one is the vector v with components a and b at the point x and y. Okay, yeah. So if you want to draw the vector v with components a and b, you have to give me the starting point. Okay, once I have a starting point, then I can parallelly translate that one in standard position over there. Okay, clear, all right? You have to say a vector at the point, a vector at the point. Okay, and so if you want to draw the vector, you need the starting point and the components of the vector. Okay, that's much better. Okay. We have a standard vector I. Okay, I is a notation from 0, 1, and j is yeah, this is a two special vector. Okay, and if it starts from in the standard position will be the will be this is I and that's a j. Okay, so any vector can be written in the form a1 0. Okay, 0b. So if you take a out, then you take a b out, then it's written as ai and the bj. So it's a linear combination of those two vectors. Now, if let's understand the addition of a vector. Okay, so let U to be A and B, V to be C and D. How about like that? Okay, how to add them together? Add them together. Just add the corresponding components together. So A plus C. Okay. A plus C, B plus D. Okay. Now, if we have a lambda, a number, a real number, okay, lambda for U will be just lambda A, lambda B. Okay. So, but how do you describe this addition in the XY plane? Okay. This is a vector U, and those are both in the standard position. So what I'm going to do is, if U plus V, so I'm going to draw the U first, starting from origin. But this time, I draw the vector V starting from the end point of U, okay? And then I connect these 2 points. So this would be vector U plus V, okay? Yeah, so this V, those two V are parallel. It's the same V, but it's different location. Okay. Okay. And the lambda U depends on the value of lambda. If that's a U, then you have to draw it lambda U. It's the same direction, maybe. It depends on if lambda is positive, so that will be lambda U. Okay, the length, just multiple. For example, if lambda is 2, so just double the length. Okay. Yeah, this is a addition. We have to understand addition multiplication first. Okay. All right, a vector field. A vector field F on a domain in the XY plane okay. How to describe it? It's actually is a family of vectors. At every point, there is a vector here. At every point, there's a vector here. Okay, at every point. Okay, this is a domain D. That's a so-called yeah. So F, okay, is a family of vectors on D. Okay, this is a family of vectors on D, such that each member is a unique vector at the point. So so that means at every point, X, Y in D, there is a unique vector at point X and Y, okay? And from this family, I should say. So of course at that point. Yeah, in this family. Okay, so basic, what I'm trying to say that a vector field, okay, a vector field F, okay, a vector field F is actually just a family of vectors. A vector field F is on D is just a family of vectors on D. Okay, at every point x, y in D, there's a unit vector, and okay, this is denoted by f x, y. Okay, in this family. So at every point, okay. Yeah, at every point, I have a vector here. This vector is denoted by this. Now, how do you describe the vector? Okay, well, the vector can be described by the two components. So if you use a component, then you can define it like this: p x, y, a function, q x and y. Okay, so those are two components, but each component depends on location of the point. Okay, this also written as pxy I qxy j. Okay, right. So how do you describe a vector field using the mathematical notation of that? Okay, using mathematical notations, and then this can be viewed as a vector valued function. Okay, this at every it consists of two components. Each component a function of x and y. Okay, but if you want to visualize a vector field, then you have a domain in a two-dimensional plane, and at every point there is a vector there. Okay, you see its object. Okay, the starting point is at the point xy, and then just that's oriented piece of object. Okay, so it's have direction, and it has starting point, ending point. Okay, but if you want to describe that vector, you have to use two functions, p and q. Okay, it depends on the point. Okay, so that's a description of the vector field. Okay, all right. So sometimes we are given the vector field just using the mathematical notation, and we want to sketch it. Okay. Okay. So here the inverse problem. Okay. So a vector field. Okay. On R2 is defined by this function negative yij x and negative yi plus xj. Okay, and then let's sketch the graph. Okay, let's sketch the graph. Okay, sketch the vector field f. Okay, on R2. How do you do that? Well, here's the point. I just needed to draw one point. Okay, so we know that. Let's understand what it is. If this is a vector with components A and B, okay, if I switch the components and give a sign, the negative sign, so that will be negative B and A, okay? So this is a 90 degree. We should know that, okay? If we understand this, then everything is fine. Okay, so that's the relationship, and the product, inner product of these two vectors is gonna be 0. So the angle theta is gonna be 90 degree, okay? So at every point here, x and y, right? So the f of x and y is going to be negative yx. Now, how do you describe this vector? First of all, you draw a vector from here, right? Right. So you get a vector from the origin to the end point. Then you have to draw the vector negative yx is going to be this one. Okay, if you start from the origin, but this time this will be start from the point with coordinate x and y. So this is my vector if you want to draw it. Okay, this will be the f x y. Okay, that's perpendicular. Okay. Okay, you have a family of vectors on the plane with the same corresponding to the same same notation here, negative yx. Okay, but we have to draw one at the particular point xy. So then first of all, at every point, right, you can draw the vector perpendicular to the direction from the origin to that point. Second, it is getting longer if the vector is getting longer if the point is getting away from the origin. Okay, so you can draw it here. Okay, you can draw the circle here, right? The here, those are the vectors, okay, and here you get the vectors getting longer because the same distance from here to here, there should be same distance. This is the longer. Okay, so that's good enough to draw the vector field in the xy plane. Okay, the length, yeah, this length and equal to that length. Okay, have to make sure when you draw it. Okay, so when the point is getting away, then the length of the vector is getting longer. So at that particular point, first of all, you draw the line and the perpendicular to that line. So it's tangent to the circle. Okay, this is my F. That's it. I don't need to draw the table of the, usually you pick up a point in the XY plane and then draw the vectors at each point. Then you see how does that look like, right? Now, if I change the problem a little bit, okay, so given vector field f x is just x and the y, okay, then then how does it look like? Well, at every point, right? This is a point, x and y. I needed to, yeah, this is actually a vector field. So that means the vector at x or y is given by this by this note here. Okay, so this is a vector at x and y. Now, if you just want to draw the vector in the standard position, okay, and it was component x and y, and that is a vector, right? Okay, so but we want to draw the vector starting point at x and y, so you just parallel translate it here. Okay, this is my vector f. Okay, and then you will see that this is always in the same direction, right? So if I draw the circle here, it's better to choose a, yeah. If I draw the circle here, and at this point, this is a vector, right? At that point, the vector is getting longer, right? And this is the point, okay? So that's, okay. And so you will see they're all going out from the center. Okay. Okay. The length, when you draw it, be careful, just cannot draw randomly. So you from here to here, if this is a R, the length of this one should be also equal, the same length. Okay, because this is a point x and y, and that vector x and y has components this. Okay, so that's why they should have the same length. Okay, the radius, if this is the starting point is on a circle with radius r, then the length of the vector should be equal to R. Okay. Okay, now let's take a look at some problems from the book. Okay, let's look at the problem number 4. Sketch the vector field by drawing a diagram like figure 5 or figure 9. Well, that's okay, just to sketch the graph. Sometimes you don't need to draw it, okay? So this is going to be, I use this notation, x plus y, okay? I don't use ij. Okay, so this is the vector, okay? Sketch the graph. Sketch the vector field on R2, okay? Yeah, it's a little bit difficult here, okay? So let's just look at the one vector. How does it look like? Then depends on location. This is a typical point, okay? So this is our B vector, right, from there, right? Okay, just let's fix the point. All right, so let's draw the vector with corresponding to x and y. So the x direction would be y, okay? So the x direction would be the y. So this is a y, right? So y is here. The y direction is x plus y. Wow, x plus y is a much larger number. Okay. So this is the sum of those two. So I have a 1, 2, something like that. Okay, it's not easy to draw. So this is my vector. Has components y, x plus y. Okay, but we have to draw it here. So the vector field looks pretty strange. Okay. Okay, we have to draw it here because the starting point is at x and y. Okay, so this is a vector. And if x and y both are positive, then this is a directional vector. Okay. Now, it's hard to imagine. Yeah, it's hard to imagine. Yeah, it's hard to imagine the vector at the other locations. Okay, so what I'm going to do is we have to use a diagram. Okay, so we can draw the diagram. Okay, so we have it's figure 5. Just look at figure 5. Okay, choose a point. Let's see, and here's the f. Okay, x and the y. This is the x and y. Okay. So we can choose a 0, 0 at the origin. When x is 0, y is 0, I got 0, 0. Okay. Okay, so it's a 0 vector. Then I needed to get 4 vectors at those four vertex of the square. No, the idea is that you divide this whole plane into many. Yeah, you got many points here. So you're trying to plot the vectors at those points. Okay, so my first one will be when x equals 1, y equals 0 at that particular point. Then when x equals 1, y is 0, and that will be this. Okay, then have to go up. Yeah, we get this first. Get the vectors on the square first. Okay, and then when y is 1, x plus y is 2. Okay, and then I have a 0 and a 1. Then I got when x is 0, y is 1. Okay, then I get -1 and a 1. And then y is 1, x plus y 0. Then I get negative 1, 0. When x is 0, y is negative 1, y is negative 1, x is 0. Okay. And finally, I get a negative 1, negative 1. Okay. And y is negative 1, that's negative 2. I think I should have a 0, negative 1, right? Total, how many points here? Around 1, 2, 3, 4, 5, 6, 7, 8. I have to have 8. Yeah, when the y is negative 1, x is 0. Okay. So, and finally, it's a 1 and negative 1. I think that will be the S one. So you around, yeah. So there are 8 points here, right? Right? 1, 2, 3, 4, 5, 6, 7, 8. So when y is negative 1, x plus y 0. So now, at least you have plus the origin, you have total 9 points. Now we are ready to draw at least the vector field at those 9 points. At the origin, it's 0, right? Okay. So imagine I'm going to use the red color here. At 1 and 0, it's going to be 0 and 1. Okay. At 1 and 1, it's going to be 1 and 2. 1 and 2 is going to be like that. Okay. 1 and 2. At the 0 and 1, at the 0 and 1, it's 1 and 1. Okay. At the negative 1 and the 1 will be 1 and 0. It's horizontal. Okay. At negative 1 and 0 is be negative 1, negative 1. So it's going that direction. Okay. At negative 1, negative 1 will be negative 1 and the negative 2. Okay. And at 0, negative 1 will be negative 1, negative 1. Zero, negative 1. Will be negative 1, negative 1. Okay. And also negative 1, 0. Let's see why it's also negative because hold on, I have a mistake here. When x is negative 1, y is 0. Yeah. When x, this will be 0. Okay, because it's a y, x plus y, right? Y is 0. So y, x plus y. So it is going to be 0, negative. It's a symmetric actually, right? So 0, negative 1. Okay, and finally, the last point. 1, negative 1. Okay, y is negative 1, and add them together, it's 0. So the first component is going to be negative 1. It looks like, yeah. So the vector field, it's pretty strange, but it looks like it's going that direction. If you want to draw the flow of the vector field, okay, it's going to be like that. Okay, clear? Yes. You know, if you draw a bunch of vectors on the XY plane, and you will see, you will see, how does the flow going? Okay, if you think the vector at the point is the velocity vector of the flow, then you can imagine how the flow goes, right? So this is it looks like fine here. That's a picture. I think that's enough. You can draw another. You can draw another set of vectors. Okay, along the larger square. Okay, then you have much more points. So then you get additional informations. But I think that's good enough. Okay. So this is a picture. Okay. This is a graph of the vector field. All right. So then let's look at the next one. Problem number 6. Okay. F is going to be yi minus xj square root divided by square root x squared plus y squared. All right. So this is a vector. You can write also like this form, y negative x. All right. So this just the normalized of the vector. Actually, this first of all, you note that the length of this vector is always equal to 1. Okay. This is going to be x squared plus y squared, square root of y squared plus negative x squared. It's always equal 1. Okay. It's a unit vector. So don't draw the vector longer, you know, it's the same length, but different direction. Okay. All right. So first of all, let's understand the following picture. Okay. If we have a vector with components A and B, if I switch the order, where is a vector with B and negative x? Okay. B and the negative x, the first component is B, so it's here. Negative x is negative A here, so it's going to be some point here. Okay, right? This is A, that's a B, right? So negative, if the first component is a B, the second component, the second component is negative A. So this will be B negative A. So this is a vector. Now, are they perpendicular? I think so, yes. They're perpendicular because the inner product of those two is going to be A times B plus B times negative A. So it's 0. So those two vectors are perpendicular. Okay. So it's 90 degrees, but just in the other, you know, it's other direction. So that is good information for us to draw the graph. Okay. Now I'm going to draw the graph around the circles. Okay. All right. So take an arbitrary point here. So this is a point X and Y. Okay. With a radius R, right? And the vector at that particular point, you have to rotate, but be careful, it's normalized. So it's a unit vector, okay? It's not like a very long, okay, when it's getting away from it. So this is a vector F, okay? And the same length here. It's the same length here. It's the same length here, okay? It's the same length here. Okay. So it's rotated counterclockwise. Okay. But the length of the vector at every point is always equal 1. That's the key point. That's the tangent to the circles. The vectors, those vectors are tangent to the circles around the circle. But they have a constant length, 1. Okay. They're not, and it is not defined at the origin. Okay, so f00 is not defined, is undefined. Okay, so there's no vector you can draw because imagine, right? How to draw that, right? Those are the vectors around the circle, unit length. Now at the origin, how do you draw it, right? So it's undefined. Right, so that's a picture of this. Now, similarly, we can define a vector field in three-dimensional space, okay? Define or describe vector fields in three-dimensional space. And even high-dimensional space, but which we cannot see it, okay? Okay, and mathematically, you have a vector field as a vector value function, okay? And they usually have three components. Right, the component, what is the notation here in the book? And it doesn't matter which notation here. So three components, okay? So PQR. So usually it's written as Q, X, Y, Z, and R, X, Y, Z. Okay, it has three components. If you in three-dimensional space, okay, if you want to draw the vector, right, and without specifying the origin, then the standard position will be always here. But if you specify the point, then that will be the vector I'm talking about. Okay, so when you draw it, so this is the F. If I already already said that this is going to be the vector at the point x, y are given by the three components, then when I draw it, I have to draw it from starting point is from the point x with coordinates x, y, z. Okay. If I just ask you to draw the vector with three components, then you draw the vector starting from the origin. Okay. If you're told that this is a vector at x, y, z, then you have to draw that one. Okay. I'm going to change the colors. This is a red one. Okay. So when you sketch the vector, you have to ask yourself, where's the starting point? If it's not specified, then just draw the vector at its origin, okay? If it's specified, then draw the vector starting from that particular point. All right, so now let's take a look at the following problem. So that's problem number 8. And that is going to be Zi, which is going to be Z, 0, 0, okay? Let's sketch the graph of this. Right. So I don't think we needed to draw the diagram here. It's obvious, right? So at every point in the space with coordinates x, y, z. Okay. So this is a height, right? So this is a point. How do you draw, right? So this is the height is z. So the vector you're going to draw, okay, the x component is going to be z. So starting from that, the x component, if this is a h, then you draw the vector parallel to the x-axis. The length is also h, okay? And that is a vector, okay, parallel to the x-axis, okay? Parallel to the x-axis. So now you can imagine you get high and high, and that vector is getting longer and longer, right? And then when getting close to the x, close to the xy plane, and it's getting 0. Okay. And now negative side would be opposite side, right? Because it's a negative. Okay, so length is the same, okay. And this is a independent of location of the point on the xy plane. Okay, so you just draw the vectors along this line parallel to the z-axis. Then you move this line over the xy plane, right? And you get the family of the vectors. So imagine it's harder to imagine how does it look. I just draw a few tangent vectors. Okay. Yeah, at the different locations, it's the same situation here. If here this is another line, okay, perpendicular to the z-axis. This is the intersection point, and then you will see that those are the vectors. Okay. Okay. All right. You have to catch the point, the key point, how do you describe these vectors, right? Yeah, the vector field is independent of the location in the xy plane. Okay, so you draw the vertical line, and you draw the vector field along this vertical line. If we can describe this clearly, then we can visualize the vector field. Okay. So it's in three-dimensional space. It's harder to draw a vector field. Honestly, you have to draw. It's much harder to draw it using because you have to draw lots of objects there, right? It's vectors. Okay. So the vector field is 0 everywhere in the xy plane. Okay. So this is the key point. F, X, Y, Z is going to be 0 on the xy plane. Okay. That's the first key point, right? And it's getting high and high, the point above the xy plane, the vector is getting longer and longer. Okay. So Fx, Y, Z is always parallel to the x-axis. Okay. Right? But it's the same direction as the x-axis if it's above the xy plane, but it's the opposite direction. Okay. So the length, third one, the length is going to be called z. Okay. The height of the starting point or the foot point. Okay, of the f. Okay, so that's good enough to describe the vector field. We sketch the graph, but I also point out some key points. It's because it's harder to read it from the picture. All right. Yeah, if you use a diagram, how many points you have to draw out of the list. That's just too many. Yeah, it's harder to do that. Okay. Unless you use a computer. Computer can do very fast. At the moment when enter all the data, you get the picture right away. That is the power of the machine. Okay. Now, human being always design, we design the machine, but does not mean the machine cannot beat us. Okay? At least in the computation right now, but in the future, okay, the machine can do better. That almost can do everything the man can do. Okay. Okay, so let's take a look at yeah, I'm not going to do the problem like matching the vector field with a picture. This probably have to do some homework like that. But I cannot do the I cannot do it here. Okay, so think about the gradient of a function. Okay, the gradient of a function, it's called the gradient fields. Okay, given let fxy be a function, okay, on the domain in R2, okay, then the gradient of function actually is a vector field, because at every point, this is going to be, right? So you got two components. So this is a vector at, yeah, this is a vector at the point x and y. So we get a vector field. We get a vector field, and this vector field is called a gradient vector field. Okay, so this, we get a vector field, which is called a gradient vector field of f. Okay, and so given a function, you get the vector field. Okay, now how describe the vector field in geometry? So think about the level curves, right, of the function f x y equals k. Okay, the gradient of f is going to be a normal vector. Okay, perpendicular to the tangent line to the level curve. So it's easy to describe it. All you have to do is just draw the, if you know how to draw the level curves, then you can draw the gradient vector field of f. All you have to do is just make sure those are perpendicular to the curve. Okay, I don't know the length, but at least I can tell they're perpendicular to the level curves. Okay, those are the level curves. So the gradient of fx is perpendicular to the level curve at every point. Okay, that's a key point. You can do similarly three-dimensional case. Okay, so let's take a look at the following problem. Yeah, given let f of x and y is going to be it is going to be square root of x squared plus y squared. Okay, so this is a function, right? And the value of the function is just the length. This actually is a distance function between between the origin and the point x and y, okay? All right, so the function is increasing when the point getting away from the origin, right? So let's take a look at the partial derivative. When I differentiate with respect to x, I will get, and that's just x, okay? When I differentiate with respect to y, I get this. Okay, so the gradient of the function is going to be this, and you notice that the length of this vector is always equal 1. Okay, it's unit vector. All right, how do we sketch the graph of the gradient field? Well, now the level curves as a circle. Okay, the level curves of f are circles. Okay, so those are the level curves, circles. Okay, and here f equals 2, for example. This f equals 1, right? So the circle was radius 1, the circle was radius 2. Okay, so how do you draw the vector field? It's a perpendicular to the circle, right, at every point. But be careful, our gradient has a constant length, so that's why I do not draw a longer one. I just always have the same size, but perpendicular to the circle. So it's easy to draw it, right? And the same here, it's the same length. It's not longer. They always have a unit. Okay, so this, you see, you get perfect picture quickly. Right? They're now getting longer. Okay, they have a unit length. And the function is not differentiable at the origin, so there's no vector gradient at the point. Okay, so this f(0,0) is not defined. Okay, why? Since f is not differentiable at the origin. Right? At its origin. It's not differentiable at its origin. But not every vector field coming from the gradient of some function. Okay, this is what we're going to discuss in the future. Okay, they're not now if the function is 3 variable, the gradient vector field is defined the same way. Okay, so let's take a look at another problem. So let f, x, y, z to be a function in 3-dimensional space. I just called x, y, z. Okay, so this is a function defined on R3. Okay, so the gradient, okay, is going to be, here's y, z, and fy, x, y, z is going to be x, z, right? F, z, x, y, z is going to be x, y. So I can write down the formula. So you get y, z, x, z, x, y. Okay. So this is a vector field. Okay. This is a gradient vector. It's not easy to draw it, honestly. It's not easy to draw it because those are components. Okay. And you can also express it in the following way. You can take x, y, z out. You will see, surprised, this will be like that. So at the point, at any point x, y, z, the product is not going to be 0. Otherwise, you cannot take x, y, z out, okay? Because one of x is not defined. Maybe one of y is not defined, okay? So in general, you see, y, z, x, z, x, y, they're all defined for any value for x and y, z, okay? But if you want to take x, y, z out, you get 1 of x, 1 of y, 1 of z, and that cannot be, denominator cannot be 0. Okay. This is a gradient. I cannot easily draw this. Yeah, I cannot draw it. And you have to draw a diagram and choose many points, and then you determine so the value components at every point. Then you get the vectors. Okay. So let's just take a look at a couple of them. Okay, this is the gradient. Okay, x, y, z, and at the origin, right? Here's x, y, z. At the origin, this is going to be 0, right? At point 1, 0, 0 is going to be x is 0, right? And y, this is 0, the product is 0, so that's always 0. Okay, so so this is the same here. Okay, they're all 0. If only one of the yeah. So plus minus 0, 0, plus minus 1. And this will be, the product. One of them must be 0. So that's why they're all 0. Okay. Now, if you have a 1 and a 1, okay, then it's a different story. Okay. So when x, and this will be 0, 0, and that'll be 1. Okay. And if here's 1, 0, 1, and I think which component is not going to 0? So x, z is not going to be 0. Okay. If this is a 0, 1, and a 1, then y, z. Okay. So let's draw a few vectors here in the xy plane. All right. At the origin, it's a 0. At those points, there are the vectors all 0, right? Okay. The vector is 0. I can draw. Okay. At the point 1, 1x, at this point, okay, the vector is going to be like that. Okay, let's use a red color for the vector. Okay, then at 1, 0, 1, which is in the xz plane. In the xz plane, the vector, the second component is going to be 1. So the rest of components there. So it's going to be like that. Okay. Then at 1, 0, 1, 1, which is the YZ plane, it's behind that. And the first component, yeah. Okay. This is in the YZ. Okay. So here's a 1 and a 1, 0. Here's a 0, 1, and a 1. That is going 1. Yeah, 1, 0, 1. Okay. I only draw the 3 vectors here. They all point in the same direction. It's funny. Okay. They pointed to the direction, the same point here, the 3 vectors. Yeah, it's harder to draw by hand, okay, because you have to, first of all, it's 3-dimensional space, which harder to describe in 2-dimensional piece of paper, okay? Then you have to draw lots of vectors. So most of the problems, if we ask you to do is a vector field on the xy plane. Okay. So I stop here. I'm going to send you the quiz. Okay, we're going to do the quiz today.
I have a